We will now look at closed-loop control systems. In a closed-loop control system, the output of the process or control variable is constantly monitored by a sensor. The sensor samples the system output and converts this measurement into an electric signal that is passed back to the controller. Because the controller knows what the system is actually doing, it can make any adjustments necessary to keep the output where it belongs. The signal from the controller to the actuator is the forward path, and the signal from the sensor to the controller is the feedback, which closes the loop. The feedback signal is subtracted from the set point at the comparator, just ahead of the controller. By subtracting the actual position, as reported by the sensor, from the desired position, as defined by the set point, we get the system error. The error signal represents the difference between where you are and where you want to be. A zero error means that the output is exactly what the set point says it should be. As an example of a closed-loop control system, consider again the robot arm resting at 0 degrees. This time a potentiometer, or a pot, has been connected directly to the motor shaft. As the shaft turns, the pot resistance changes. The resistance is converted to voltage and then fed back to the controller. To command the arm to 30 degrees, a set point voltage corresponding to 30 degrees is sent to the controller. Because the actual arm is still resting at 0 degrees, the error signal jumps up to 30 degrees. Immediately, the controller starts to drive the motor in a direction to reduce the error. As the arm approaches 30 degrees, the controller slows the motor, and when the arm finally reaches 30 degrees, the motor stops. If at some later time an external force moves the arm off the 30-degree mark, the error signal would reappear and the motor would again drive the arm to the 30-degree position. The self-correcting feature of closed-loop control makes it preferable over open-loop control in many applications, despite the additional hardware required. This is because closed-loop systems provide reliable, repeatable performance even when the system components themselves, in the forward path, are not absolutely repeatable or precisely known. This ends our quick presentation on closed-loop control systems. Let's go see how they're applied.